You guys are good, you know all of it. You're so ready, you're just like, you know what, I'm just gonna go to the football game tomorrow. I'm gonna sleep all day on Sunday, I'm just gonna show up Monday morning, I'm gonna crush this. No studying all weekend. Okay. That's what I would have done too. When I was in y'all's shoes, I could never motivate myself to do things very far in advance. So I appreciate and resemble those of you that have maybe not done as much as you would hope to, or anything at this point. I was very much, I'm just gonna say the night before kind of person. And most of the time that ended up, I managed to pull it off, but sometimes it didn't, and then I would hate myself and, you know, a lot of self-loathing in the midst of that, so. Okay, Garrett, you had a question.
Yeah, what exactly do we need to know about myosin ATPase?
What do we need to know about myosin ATPase? So let's start with this. Where is the myosin ATPase? Somebody said it back there? On the myosin, good, that's a good place to start, okay? Myosin ATPase is an enzyme that sits on sort of the head of the myosin near where it connects to actin. Okay. The job of a myosin ATPase is to break down ATP. It cleaves ATP into a molecule of ADP and a molecule of inorganic phosphate. Okay. That has to be done in order to this very, very last step in the cognition to contraction down here where it says back to the high energy state. Once ATP comes in and binds to myosin and causes it to let go of the actin molecule after you've done one sort of cross-bridge cycle, then the myosin ATPase breaks it in half, and that shifts the head of the myosin back to what we call the high energy state, which is where it's basically kind of cocked itself back. It's ready to be able to grab on again and pull and do another power stroke. One other really important thing, though, about myosin ATPase. It is one of the key things that determines this particular parameter, or this particular idea. Anybody remember what that is? Fiber type. Okay, fiber type. And Landry, what were you mouthing? Yes, that's exactly right. It determines fiber type by the speed at which it will break ATP apart. That's where we get fast twitch versus slow twitch. It's because of the speed of the myosin ATPase enzyme. Okay? So it plays this key step in the cross-bridge cycle. But different fiber types run that step at a different speed, and that determines some actual functional properties of your muscles. If you have more fast twitch fibers, you can contract those muscles faster. You can generate more power, which means you can sprint faster. You can jump higher generally. Okay. So that's what I want you to know about the myosin.
For muscle organization, would you prefer like the order, or do you want like more so us to know like the function of the myofibril, or just like that it doesn't?
For that, it's really just sort of big picture muscle, fascicle, fibers, myofibrils, sarcomeres, proteins, just that general kind of paradigm of how it's organized in that way. Okay, that's all that I really, because most of the stuff, right, that we talked about is on the fiber or the sarcomere level. So if you know the individual structures there, that you kind of have to, as we get into all of this, you're gonna be good. Okay. But if you know the other part, like if you were to dissect the muscle, be like, it's the whole muscle, there's a fascicle, that thing. That's really all I want you to do. Okay. Question here. Yes, Melinda.
In terms of the torque.
Yep.
And how it supports.
Yep.
You kind of told us that different angles are stronger and weaker, but why are they stronger and weaker at those angles?
Great question. Okay. So let's start back at the first part. You guys remember, torque is force produced by a muscle multiplied by the moment arm or the lever arm that is the distance from where the tendon that connects to that muscle, from where the tendon inserts to the axis of rotation of that joint. So in my knee, it's the distance from where the patella tendon inserts down here on the tibia back to right here, the axis of rotation in my knee. Okay. So if we make the assumption that my knee extensor muscles can generate the same force here, here, or somewhere in between, but we know that torque changes. Torque is less here, greater in the middle, and then less out at full extension again. If force is the same, I know that we don't like math, or some of you don't like math. The algebra tells us if force is equal but torque changes, what's the only other parameter in our equation that has to change? The moment. Okay. Torque is force multiplied by the moment. And so if I get less torque at sort of lots of flexion here, it means that that moment arm is shorter. The moment arm is smaller here. As I move into the middle, the moment arm lengthens. Okay. And then as I get out to full extension, it shrinks back down again. And that's all because of the amount of stretch and just the anatomy and how the joint articulates in relation to where the tendon is. Okay. And that may be kind of a weird concept to think, but it's in the same place. And as I do all of the tendon at the elbow, as I do this, how is that distance going to change? And that's well beyond what we need to sort of know for class. I just want you all to know that it does and it can change. So that's why, with the same muscle size, with the same recruitment, with the same firing rate, at the same contraction velocity, joint angles still matter. I'm weaker at some joint angles, or I apply less force to the tibia in my knees at some joint angles versus others. Some of you are stronger than others at different joint angles because you have a longer moment arm, because of the individual anatomy of what your joint articulations look like and where your tendons insert. You're able to better apply the force from your muscles. That's one of the things, right, that can also contribute to why you have smaller muscles than someone else, but yet you're still stronger, or you work out less than them, but you're still strong. Like that also is going to play a role. Okay. And you can't really change that. What else? Okay. Let's talk about this again. Okay. This is the force frequency relationship. Okay. And sometimes, and I wrote it up here, we sometimes call it frequency. We sometimes call it firing rate. Okay. What it really is, very, very simply, is the number of action potentials that the motor cortex is sending down the spinal cord that are reaching the alpha motor neuron and therefore are reaching the neuromuscular junction and the sarcolemma in a given amount of time. Okay. I'm getting 5 action potentials out of the nervous system every second, or I'm getting 10 or 20 or 40 action potentials per second. Okay. So that's the initial part. That's how it fits into this. Okay. Now, I get 1 action potential. It fires all the way down through all of this, and that gets me some amount of calcium that is going to be released out of the sarcoplasmic reticulum. Okay. Now, I didn't put it up here, but I release the sarcoplasmic, I release the calcium from the SR. But then it immediately begins being pulled back inside back into the SR. So I'll try to draw this in a different way, okay? Remember, not an artist, but muscle fiber, okay? There's the sarcoplasmic reticulum, okay? I'm gonna draw this deal. I'm just gonna draw like the top half of it, okay? Here's a T-tubule. Okay, this is the sarcolemma. So we're gonna get acetylcholine that binds on its receptor. I get an action potential on the sarcolemma. It runs down the sarcolemma, down into the T-tubule, right? Where it is going to then activate the DHP receptor here, which then opens the ryanodine receptor there, and calcium moves out into the cell. Okay. One action potential. So we'll do some math to try to illustrate this. Again, I'm sorry, I know math, it's terrible. Let's just say for every action potential, I get 10 molecules of calcium released, okay? This is a completely made up number, completely made up, not real. Okay, it's just for easy math for illustrative purposes. So this gets released. So now I have 10 molecules of calcium floating around inside my cell. Okay. That calcium binds to troponin, it pulls tropomyosin, we get cross bridges. We're getting some amount of force production out of these 10 molecules of calcium. There is another enzyme that sits on the sarcoplasmic reticulum, and this is called the SERCA enzyme. SERCA is what's also called the calcium ATPase. So this enzyme uses ATP, and its sole job is to take these calcium molecules that are outside of the sarcoplasmic reticulum and pull them back in. Okay? Pull them back in. SERCA is, just think of SERCA like a vacuum cleaner. Okay? It's like a vacuum cleaner. So you release them and then it vacuums them back up. SERCA runs at a certain speed. It has a capacity to pull a certain number of calcium back in, let's just say every second. Okay? So let's say that SERCA runs and it can pull, I don't know, it will pull 5 calcium molecules back in per second. Okay. So I get an action potential, I release 10. 1 second later, there's now only 5 that are left because 5 have been pulled back in. Okay. So what happens then? So now I'm just going to draw this in here. I've got 5 from the first action potential. If I send a second action potential down through all of this, and it arrives 1 second after the first action potential, I've got 5 calcium molecules still out. I get an action potential here. I release 10 more. Now I have 15 that are out in the cell. Okay? 15 is more than 10. If there's more calcium, there's more chances to bind onto troponin. I will get more cross bridges. If I get more cross bridges, I get more force. Okay? Does that part make sense? I now have 15. Okay? 1 second later, right? I now, instead of having 15, I'm now down to 10. I get a third action potential. I release 10 more. So now 3 seconds after I started, I've got 20 calcium molecules instead of 10 or instead of 15 that are in there. Okay. That is what this relationship illustrates, is that if I send a second or a third or a 20th action potential down to the muscle fiber before the SERCA enzyme has had a chance to fully pull all of the calcium that's out there back into the sarcoplasmic reticulum, When the next action potential arrives, there's some leftover calcium inside that fiber. Plus, then we're going to add on whatever that next action potential tells us to release. So we get more force. Okay. It looks like this. Now, on this very, very top end, at some point, okay, I send so many action potentials, and they're so close to each other in time that I get a big enough signal that I release as much calcium as I can. And it's constant, and basically Circa has no chance to pull things back in because there's so many action potentials that are coming. And so now all the calcium that's in the sarcoplasmic reticulum that can be released, it's all been released. So of course, plateau off even if I send more and more action. I've maximally released calcium from there. Okay, Joey.
The set speeds, what would it be in like a type 1 fiber versus like a type 2X and type 2M?
Good. My next point. Okay. Just like the myosin ATPase, Circa, the speed of Circa, okay, the capacity of the vacuum cleaner to pull stuff back in is different between fast and slow twitch muscles. Fast twitch fibers have a Circa that pulls calcium back in faster than slow twitch fibers. So if a slow twitch fiber operates at 5 calcium per second, a fast twitching operates at 8, let's just say, calciums per second. So what that does then is it can shift the way this curve or this relationship is going to work. Okay. In slow twitch fibers, they will tend to reach peak calcium release somewhere between maybe 20 and 30 action potentials per second at about 20 to 30 hertz. Fast twitch fibers, it may be more like 50, 60, 70 hertz. It can be almost double. Okay. And that's because the Circa enzyme functions differently. Okay. So if I drew that out, I'm going to redraw this relationship, okay? Oh, didn't do that right. Okay. It would look something like this. Slow twitch fiber reaches peak at a lower firing rate than a fast twitch fiber does. Okay? Because the Circa works better. How many people are confused? No one? So I should definitely ask this question on Monday. This should definitely be one that I ask. Okay. Any other questions? This is your chance. Yes, Emily.
For force modulation, like that stuff, what do we have to know about it?
Not a lot. Basically, that we modulate force mostly through recruitment and firing rate, right? Like you've turned the muscle on. And if I need a little bit more, a little bit less force, I'll either recruit or turn off additional motor units, or I'll play around with the firing rate. So I'll send and I'll get a little bit more, a little bit less calcium that's going to be released, and I'll adjust force in that way. That's really all that you need to know. I think there's something in the slide about like small muscles mostly use firing rate and big muscles mostly use recruitment to modulate force. I'm not going to ask you about that. Like that's a little, it's probably a little far beyond from a motor control standpoint, what we really, really need. Okay. Of course, sure.
For the force velocity relationship, could you explain the eccentric and isometric? Concentric is again the increase your force and velocity go down, but everything's.
Does an isometric contraction have any velocity? I assure you that will appear in some way, shape, or form on the test. Okay. Isometric contraction has no velocity, there's no movement. Okay. The force velocity relationship is entirely explained by the cross-bridge cycle. 100% explained by the cross-bridge cycle. Okay. So, in order to move concentrically and go faster, I have to speed up how often I break the cross bridges apart. So if I break them more often, I break them faster, there's fewer that are attached at any moment in time, therefore there's less force. If I have no velocity, it's isometric. Do I have to break cross bridges, or can I just engage them and then say, right there, hold on? Okay, that's what happens in an isometric contraction. So if they never have to break, I get more force because I can, in theory, hook all of them on and just sit there. Okay. Because they don't break, that also means it doesn't cost me very much energy because we use the ATP to break them apart. Okay. Eccentrically, it's the same concept as the isometric. Okay, that the cross bridges get formed and they engage. But because we're lengthening the sarcomere, we also don't have to break them apart. Because if we break them, they're going to want to go back to help us shorten. So eccentrically, they engage, they hold on, and then we let gravity win by producing ever so slightly less force than we need. And it tries to pull and stretch that muscle out. As it stretches, the connective tissue, right, endomysium, paramysium, epimysium, tendons, ligaments in those joints are elastic. And so as I am standing here not doing anything, my patella tendon is attempting to prevent gravity from pulling my lower leg down. It's like a rubber band, right? It has some ability to generate force, or at least it takes a certain amount of force to cause it to deform and stretch out. So it provides, our connective tissue provides some extra force generating capacity to resist against gravity. So I get cross bridges that lock in and I get force from that. Plus there's extra force from the elasticity in our ligaments, tendons, and connective tissue. And that's why I can get more force than I can isometrically. But again, because the cross bridges don't have to cycle and break to get lengthened, I don't lose force as velocity increases. It's all about the cross bridges. Okay, Emily.
So like between isometric, concentric, and eccentric,
Uh-huh.
will we have to know which one like creates the most force or
Yes.
which uses the least?
Yes, absolutely.
You want to answer?
Sure. Concentric generates the least amount of force and costs us the most energy. Isometric is right in the middle. You get more force than concentric and it uses less energy than concentric. And then eccentric gets us the most force, and it's probably in some ways debatable the amount, if it uses less energy even than isometric, they're probably reasonably equivalent, right? But that's how that's going to go. Think about it this way, right? Think about it as either I'm doing a curl and I'm holding something, or I'm going up and down stairs. To go up the stairs, right, costs me the most energy, and I can carry the least amount of things up the stairs. Isometrically, I'm just standing on one stair. I'm standing there. I can hold my big backpack or whatever I've got. I'm standing. Okay, it doesn't cost me that much as much energy as going up. I can hold more there than I could ever probably take another step with. Eccentrically, I'm going down the stairs. I can carry even more, and it still doesn't cost me hardly any energy, right? Like, or you can think about it, right? Like I'm doing a curl, right? Whatever I can pick up, if I did multiple reps picking a weight up, I can just hold that weight there longer, just standing there, just hold it isometrically, or I can lower it down way more times than I could ever hope to pick up. Okay.
Are you wanting to ask about power by fiber type?
Yes. Yes. Power by fiber type. Okay. Power is force or torque multiplied by the contraction velocity. So, if fast switch fibers generate more force and they can go faster, which ones are going to be more powerful? Type 2s. Okay. And not just a little bit more powerful, right? A shit ton more powerful. Okay. That's why, right? Cross country runners aren't jumpers, right? True like marathon runners are not jumpers. They can still sprint pretty well, but they're really not jumpers. They got a lot of slow twitch fibers. Okay. And that's why people that are good sprinters tend to also be really good jumpers. We don't see it as much now, but it used to be in the Olympics, like the men and women that were the best, like 100-meter runners or 50-meter runners were also the folks that would long jump and do those kinds of things because both require lots of power. Okay. It's the same thing. Okay. And we can train we'll talk about this, we can train your power a little bit by training you to maximize recruitment so you can get all the muscle turn on, and we can train you a little bit to go a little bit to recruit a little bit faster. But a lot of it, it's just fiber type, right? I am mostly a slow twitcher, and I am, I was about as fast as I could be for the fiber type that I had, and I can't jump at all, right? I can't do it. So it was a terrible revelation for me when puberty hit. And I was like, why am I not the fastest kid in my class anymore? It was very, very bad. So probably kept me from playing baseball at the University of Arkansas. If I had a little more fast switch, I could run a little bit faster, then I probably could have gotten to play there. But that's just my 46-year-old self being nostalgic about way old things. Y'all are familiar with the movie Napoleon Dynamite at all? Yes. That's me being Uncle Rico, just a little bit in those ways. So my remembrance of what things were like is probably not 100% accurate. So don't worry about it. It's just the angle at which the fibers come in and connect to the tendon. And if you have multi-pinnate muscles, you get more force because you have a larger functional cross. I mean, that's space.
So more angles,
more things. The angle actually, okay, so you suckered me into it, Jay. This is my own fault. By coming in at an angle, we have to do some trigonometry. Again, more math, right? Sorry. You have to do some trigonometry. We got to resolve some vectors and things as I duck. You actually lose force by having pennation because if like the patella tendon is pulling this way and it comes in like this and the fibers are trying to pull in this direction, there's a little bit of horizontal and a little bit of vertical. And so I lose, not all of my force gets transmitted exactly in line, right? This is a quad. Your bicep or your hamstrings, they're right down here and they're pulling directly. But it comes in like this. And so I can go here, 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 and then it rotates and it comes in from the other side as well. And so I can, by having an angle, I can pack way more fibers in, which overcomes that little bit of that 10 or 15% loss of force from the angle, because I've got way more fibers in the same kind of area or volume, basically. And that's why it's so useful that particular way. But that's really, in some ways, like, that's like the honors class version of what we're doing, or that's sort of the master's degree kind of level of things for us to know. But if you want to see that, come to the lab and we'll get Kellowan's ultrasound out and we'll put it on one of your muscles and we can show you your pennation angle. Like you can capture the screen, you can just measure it. It's super easy. Right? It's super duper easy. We had a group that did it in Capstone one year. Any of you guys in Capstone? How many of you want to need to take capstone next semester? How much? Oh no, wait, y'all can see shit today. It's not fun, I'm like, how much? How many Dr. Peppers will you buy me if I tell you who's teaching which section of capstone? Because as soon as I get back to my office, the names, they're actually not 100%. I didn't even look at the times yet. I just put them in yesterday to know who's doing it. We're gonna take the names off. And you guys just have to join the one that fits your schedule the best. And then find out at the big reveal on the end. Because there's gonna be 5 sections of capstone. So, yeah, there's only 2. We have way more spring grads than we do fall grads, the way it mostly works. So I can tell you who's doing it, but I won't tell you who's doing what class. How many Diet Dr. Peppers will you guys, as I'm videotaping myself, would you guys bribe me with to know? You can see it's in the book, y'all can see it right now, but it's not right. I promise you it's not right. I was just putting names in yesterday so that I would know that these are the people that are going to do it, but they're not in the right sections. Clearly, at this point, we have done exactly what I was worried we were going to do, and yet I am powerless to say no. And we'll just spend the rest of our time answering questions. We'll not start the new stuff. And in doing all of this, we may even just skip the sensory motor stuff completely. And just not even cover it. I'll think about that before Wednesday. So Mallory had a random question, and then Audrey will get you next, okay? Oh, it's unrelated to class?
It's about that.
It's about this, okay.
Is that like enzyme kinetics? Is it following?
Is this enzyme
Like
kinetics?
it's following the curve?
It looks like a Michaelis-Menten plot, but it's not. Well, no, I said that. That's not 100% right, because Circa is an enzyme,
Yeah, that's why I was curious.
but it's not. No, because if it's a Michaelis-Menten plot and it's enzyme kinetics, it's about concentrations
That's what
and those things. Don't forget that though. In about 3 weeks, that's going to explain enzyme kinetics. Explain why people that are more aerobically trained and have more mitochondria metabolize. They get to eat more Chick-fil-A. They metabolize fat at a much greater rate. It's all about enzyme kinetics. That's all that it is. So we'll come back to that. So don't think. But that does look like enzyme kinetics. Yes. Who's had anybody had biochemistry? Was it terrible? Did you take it here?
Yeah.
No, I took it at UCO.
Okay, UCO. Okay. Who did you have, Emily?
Since.
Oh, sorry.
Okay. I'm not saying that we took the biochemistry class out of our PhD curriculum because of a certain person. They switched who was teaching it. And we were basically told, oh, if you haven't had organic chemistry, you're going to fail, which turned out to be correct on things. But all of this, like everything is biochemistry. Metabolism is biochemistry, right? It's all enzyme kinetics, receptor stuff. It's all biochemistry. So it's really good, but it's also can be kind of complicated in that way. I hated organic chemistry, loved biochemistry. I do still have PTSD about having to memorize the structure of all of the amino acids and all of the steps in glycolysis with their individual structures and where the enzymes would bind and all of that. Because I clearly use that every day of my life. So all of that to then not take the MCAT. Oh, the things I put myself through. Okay, I'm sorry. Audrey, you had a question.
Yeah, I was just quickly wondering about the neuromuscular junction, like how that action potential can like terminate and stuff like that with like the primary and secondary flow.
Okay, so we got lots of boards. So I'll draw a different. Okay, neuromuscular junction. Okay. Nerve side, muscle side, right? We've got an action potential. It's rocketing down the axon. Here's our voltage gated calcium channel. Action potential hits it, calcium comes in. you have all of these little vesicles down here, right? That have acetylcholine in them. Y'all need to yell at me, I drew the muscle side wrong, didn't I? It really should be, we'll do this. Okay. Primary cleft, secondary cleft, so we get acetylcholine here, we have all of these acetylcholine receptors. It binds to the acetylcholine receptor, zoop, there goes an action potential, okay? Now, Audrey, your question is, how does this get turned off? Really, really quickly, okay? Does anybody remember what is the enzyme that detaches acetylcholine from its receptor so we can shut all of this mess off? Acetylcholinesterase. Okay, please don't ask me to spell that, but it's acetylcholinesterase. So much like what happens with Circa and the calcium, there is, right, all along here, along the secondary cleft. Okay, we have this basement membrane. And embedded in the basement membrane is the enzyme acetylcholinesterase. Acetylcholine binds. Technically, takes two molecules to bind to get it to open the sodium channels, but it binds. And then almost immediately the acetylcholinesterase says, okay, get out of here, right? Like you bound, high five, go away, okay? And then it cuts it off, and then the acetylcholine usually floats back up into the junction and gets taken back up onto the nerve side into the gluton, okay? And so, because we have all of these receptors, because we have all of this surface area, it allows us to only release the most minimal amount of acetylcholine, capture it, get an action potential, and then shut it off almost immediately. Okay? That's how it's gonna get turned off. So then, if I want to keep getting more and more signals and more action potentials, I gotta keep sending them down here to tell it to keep releasing the acetylcholine because it binds, it gets cut off. Here comes more, it binds, it gets cut off. Boom, 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 over and over again. And then that way, as soon as basically you want to stop doing something, as soon as you stop sending signals from here, it's almost instantaneous then wherever it is here that this is going to get shut off there. Right? That lets us stop. That lets me stop turning the wheel this morning to not ram our car into Ellis's little friend's mom's car in that way. So my wife was like, what the hell are you doing? And I was like, 2 hours of sleep. You probably should have driven. So, and my wife hates to drive. So I end up driving everywhere. Okay. Good question. We got about 5 minutes, guys. Now, what I will tell you guys on Monday, I will get here early. If you guys want to come at like, I don't think there's anybody in classes. If you want to come at like 8:30 and start, you're welcome to. Okay, you're welcome to. For those of you, I know there were some that I initially got that you take the test like at the ADRC or someplace. I have not, that I can remember, gotten the sign up thing to email them the test if you're going to go take it there. So if that's the thing that you do, please remember to go ahead and put all of that stuff in so I can go ahead and get it to them today so that they've got it and you're ready. Okay. We still got 5 minutes. Y'all have to have more questions. Now, Joey knows everything. I'm going to pull the test up right now. You want it? No? Okay. Yes, sir.
I do have a question. So energy is used when the cross bridges are broken, right?
Correct.
Thinking
So
of
backwards.
An isometric contraction. I've been thinking of that like bar hang challenge. Are you familiar with that? So like your muscles aren't moving during that. Why do you get tired so quickly?
The honest answer is your muscles are moving a little, right? Because like you're there and you're doing a little bit, okay, in the midst of that. And we say when you do an isometric contraction that they don't break. That's not 100% accurate. They are breaking a little. Some of them are breaking a little bit. Okay. It is not just completely, like you still use some energy, but you're also using energy to run the circuit pump. right? We haven't talked about that. You're also using energy to run the sodium potassium pump. So as you keep firing all of these action potentials down, in order to continue doing that for a prolonged period of time, you're using energy to run Circa, you're using energy to run the sodium potassium pump. There's an argument at rest that we spend like a third of all of our daily energy expenditure at rest is running sodium potassium pump to repolarize our nervous system and things. That feels like an overestimate to me, but so you're still using energy. Okay, so it's a bit of a misnomer to say just because they're not breaking very often, at the myosin ATPase, we're not using as much energy, but we're still using plenty in other places to continually contract. And eventually, right, you're hanging, depending upon how close you are to your maximal force to hold yourself. We may eventually swamp by doing this your metabolic pathway's ability to provide enough ATP to keep running the calcium ATPase, to keep running the sodium potassium pumps, and provide that little bit that we need at the myosin ATPase. Okay. Right, because if you guys remember, for some of those neurotoxins that you guys did, right? I think it's the puffer fish one. Is it the tetrodotoxin or the acetylcholinesterase inhibitors, right? That you just get wide open acetylcholine. So what happens is you cramp after being bitten by that fish or spider or snake or whatever it is. You cramp, and you just cramp until the muscle fatigues, and then the muscle can't contract anymore. And if that happens to be your diaphragm, you can't breathe because you can't relax it, and then it gets tired, and then you can't breathe because you can't make it contract, and you suck. And that's how some of that stuff works, right? So blocking the contraction at different places, sometimes it blocks it by it makes it contract, and then you get tired. So seems a pretty terrible way to go. Okay. We got a couple of minutes. Anything, guys? I will be around all weekend. I'll be in my office most of the rest of today. Send me an email, send me a text message, right? Let me know what's happening. I'm happy to answer questions. We'll see you Monday. Everyone's going to take pictures. Yeah. You're very welcome. Oh, okay.
We get more time with us? Oh, really?
But if you also want to get here early and ask questions, or you want to get here early and you want to keep, like, people will get a test and we'll make them come sit down here. And then everybody can keep looking at stuff if they want, but you guys just have to sit in the back.
Okay.
Basically, so you can start if you want, you can have more time that way, if that's gonna make you feel like better and more comfortable. We'll do that.
Okay.
Okay. Because I can't give you time on the back end, because
Right.
I'm surprised that the calculus class isn't already trying to crowd in here and make us feel weird. So,
I have a question about this. For
Yeah.
the, where you're going to actually take like the. What else, like specific. Like, you know, actually exactly what you want. or-
that is exactly what I want.
I think so.
Okay, and like. through-
That.
Yeah.
Okay.
Now, if I ask you to draw a cross-bridge cycle,
That's too far.
it's the back end, but there's a little more, right? There's a slide, it's a little bit, there's a few additional details on the cross-bridge cycle. If you look at the short answer question, you ask about
Yeah.
where is ATP, where is inorganic phosphate, like what exactly is going on with those that would need to be added in. But that is like those things from, we get a cross bridge to we break it and it goes back to the high energy side, like those are the 4 steps that are there.
Okay. Cool.
Yes, sir.
Can I read
Okay,
to
I
you
was
one of
okay.
the answers?
Like, I don't know.
Yes, of course.
Alright, it's about the bicycle backwards eccentrically versus the forwards concentrically. Since the phone pedaling the bicycle forwards is conducting a concentric movement, this means they are producing less force with more energy due to the continuous detachment and attachment of cross ridges during the shortening of the muscle.
Hmm.
The total amount of cross ridges that are active determines the amount of force a muscle